The DNA molecule is the sugar, that is the 3' side. And at the end of the molecule is the phosphate, that is the 5' side. When DNA is being read, it will always be read from the 3' to the 5'. So let's say that we have some DNA replication going on, and the molecule looks like this. We know that because this is the sugar up on the top, that's the 3' side, and down here it's a phosphate, so that's the 5' side, right? So this is our template strand, and we're creating another complementary strand. That's going to look like this, right? So there's going to be, first of all, a phosphate at the top, and then so on and so forth. So with the complementary strand, what's at the top, the 5' or the 3' side? The 5' is. Now, the reason that I mention this is because when we're reading and when we're constructing, those are opposite directions. When we're reading this template strand to make new DNA, we're reading it from the 5' to the 3' side. But when we're building the DNA, this strand, we're building from 5' down to the 3' side.
I don't get that.
What's that?
I don't get that.
You don't get that?
No.
Okay, well, let's talk about it again.
Can you repeat it though?
You betcha.
Okay.
You betcha. So when we're reading DNA, we're reading from the 3' to the 5' side. Does that make sense?
Yeah.
Okay, and the way that that reading actually looks is there's a protein that's just moving from this side down to this side. Now we know that at the end, what we're going to want is complementary strands, right? And those complementary strands run in opposite directions. So if the 3' side is at the top on this one, the 3' side has to be at the bottom of this one. And if the 5' is at the top here, 5' has to be at the bottom.
So it
here.
doesn't always have to start with 5?
No, I mean, it doesn't really matter which side
Oh,
is
okay,
which.
that's what I was getting. Okay.
Yeah. So when we're reading it, we're moving from 3' to 5', but when we're building it, that building is going from the 5' down to the 3'. Does that make better sense, Sophia?
Yeah.
Okay. Okay, you cool with that? All right, so let's actually talk about the process of DNA construction. Now, I'm going to blank out the screen, and we'll go through the PowerPoint presentation after I've drawn a diagram, which I know you guys love. After I've drawn a diagram on the board. You guys okay if I erase this stuff over
Can I
here?
get a picture real quick?
Yeah, you bet. Anybody else? All right, so, sorry, I'm going to move all these other markers, which I should probably use when I'm going to. Move them all over here. I can think about using other people's pens. Look at it. Okay, so our DNA, when we're replicating it, is going to look something like this. Yeah, it's a double helix that's been separated at one point, right? And we know that when we're reading our DNA, we're going to move from 3' down here to 5' over here. Now, if this is 3' at the top, what does this have to be? It has to be 5'. And this has to be 3' over here, right? Okay. Now it'd be really cool if in our DNA it was just like one big long zipper, right? Where we start right here and we just start unzipping down this way. And we just use one molecule to unzip the entirety of the DNA molecule. And we just replicate behind that zipper. But that's not the way that it works. We're a little bit more efficient than that. We pick various spots within the DNA to start replication. So you can have replication events at various spots across all of our chromosomes. And so this is going to be somewhere in the middle of a chromosome. Now the first thing to happen with DNA replication is an enzyme called helicase comes along and physically acts like a zipper. It unwinds and it unzips the DNA molecule. It breaks those bonds, those hydrogen bonds, in between complementary nucleotides. So it unwinds and unzips DNA. Okay? So helicase is always going to unwind and unzip on this top strand, which is called the leading strand, from the 3' to the 5' direction. So helicase is always going to move in that direction, from 3' to 5' on this leading strand. Okay? That means it's not going to unzip this way. That's an important thing for us to remember. Okay? Now, the things that's holding complementary nucleotides together are hydrogen bonds, which are a weak form of an ionic bond, right? And those things form spontaneously. And so helicase is working really hard to unzip our DNA, but if we don't do anything, because these bonds form spontaneously, as soon as helicase moves beyond it, it's just going to reform. Those hydrogen bonds are going to reform. So what we have are a series of proteins called single-strand stabilizing proteins that attach to the DNA to keep our DNA separate. So single-strand stabilizing proteins. So I'm not going to write what they do because that's what they do. They stabilize the single strands, right? So they're actually going to attach right in here. And I'll draw them in red. So we get little proteins laid down that are stabilizing, I'm going to say single strand stabilizing proteins, SSPs, that stabilize those two single strands. Okay. So all we've accomplished so far is separating complementary strands, right? What we need to now do is start replicating these single strands. So the first step in DNA replication is the activity of another enzyme called primase. And primase applies, and this is important, you guys, primase applies an RNA primer, not DNA, but RNA primer. And really, a primer is just an attachment site for another protein that we're going to talk about next. Okay? So it's like a landing pad. It's just facilitating the attachment of some subsequent enzyme. So what's going to happen is primase comes in here and it applies an RNA primer. And I'm going to draw that RNA primer in orange. Forgive me, it'll look a lot like the red. But it just applies an RNA primer. All of a sudden we have a problem, because our complementary stranded DNA isn't DNA, it's RNA. We're going to need to come back and fix that, but not just yet. Okay, so primase comes in and it applies a primer. the next thing to happen is a molecule that's actually going to start attaching DNA nucleotides. And that enzyme is called DNA polymerase 3. That's Roman numeral 3. DNA polymerase 3 attaches to the primer and then starts lengthening out that primer with DNA nucleotides. Okay, so DNA polymerase 3, and I'm going to draw a complementary, I'm not going to use green, applies a complementary strand of DNA nucleotides. And it just grows it out continuously in this direction. This is the activity of DNA polymerase 3. Okay, so you guys, this green stuff, that's not DNA polymerase 3. Those are DNA nucleotides. But that's what DNA polymerase 3 is doing. It's applying DNA nucleotides. So, question, before we actually finish up leading strand replication. This right here of the complementary strand, is that 3' or 5'?
5.
It's 5. Why is it 5?
Because it's first.
Yeah, it's complementing
Because
this.
it started.
Yeah, it's complementing this one, and this end of it is the 3'. So this has to be 5' right here, and it's growing in the 3' direction. Does that make sense?
Mm-hmm.
Okay. If I ask you guys to regurgitate this for an exam, please make sure that you get your 3 and 5' correct. Okay. Now the last thing that we need to do is have another polymerase, and this is called DNA polymerase 1. It comes back and it exchanges all of those RNA primers for DNA primers. So it replaces RNA primer with DNA nucleotides. So RNA polymerase 1 is just going to come back here. It's going to take off all of those RNA nucleotides and replace them with DNA nucleotides. So that's what DNA polymerase 1 does. But please remember the sequence, right? We separate, we stabilize, apply a primer, DNA polymerase 3 grows that primer out, and then DNA polymerase 1 comes back and replaces all of that RNA stuff with DNA stuff. So if we think about this continuing, helicase is going to continue to unwind and unzip the DNA molecule in this way. And DNA polymerase 3 is just going to be able to follow right behind helicase and just continue to replicate out that template strand. Okay? So all of this is called leading strand replication. And that's awesome for the 3' to 5' direction. So let's think about replicating this strand down here. It's inherently problematic. Wouldn't it be really cool if we could just follow helicase on the bottom as well? and just grow it out that way. Why can't we do that?
Does it start with 5?
Yeah, because we have the 5' over here. And DNA polymerase 3 can't read 5' to 3'. It can only read 3' to 5'.
So the
So-
opposite?
So yeah, when we grow this bottom side, it's going to have to grow out this way. But why can't we just grow it out continuously that way? Which way is helicase unzipping it? That way. So if we start growing it out this way, there's a positive stop. We can't go beyond that because helicase isn't unzipping anything that way. Does that make sense? This doesn't change. That stays the same. Helicase only moves 3' to 5'. It's going that direction. So when we replicate what's called the lagging strand, and that's this bit down here, we have to do it in sequential units. So helicase is unzipped this much, so that we create a little section right here, and that becomes 1 unit of creation. And then helicase is going to continue to unzip that way, and so then after it unzips that way, we create another section that starts here and moves back and meets the first one. And then it unzips a little bit more, and we create another one, and it grows back and meets that second one. Should we see how that actually looks? Maybe that'll make some sense. Okay. No, let's stop here, because talking about lagging strand replication is going to take us more than 5 minutes. So, what questions do you have so far about leading strand replication? Yeah, Linda.
So just to clarify, so the helicase goes from the 3 to the 5. So then on the bottom part, as it unzips it, it goes to 3 to 5. So that top process is just replicated on the bottom. It just comes.
Kind of, except that helicase is only reading this top strand, so there isn't going to be
Okay.
unzipping in that direction. There's
Okay.
only going to be unzipping in this direction.
Okay, so the top is only the unzipping.
Right, so helicase is only moving in that direction.
Okay.
So
Yeah.
leading strand replication is a continuous process,
It
but
is.
whatever the bottom one is happening in segments?
It is. Yep. And those segments are called Okazaki fragments.